All right, so vectors are not brand new for any of you because you're very first introduced into vectors in geometry when you were talking about transformations. That's where vector notation comes up. You learn what they are and what they mean and all that good kind of stuff. And then they come back in physics and in pre-calc. So we first get a definition of a vector, which is just that it is a quantity that has both magnitude, which is size, and direction. Okay. So magnitude and direction. Besides geometry and physics and pre-cal, where have you heard that phrase? Anybody? Despicable Me. The villain in Despicable Me, his name is Vector. They didn't just misspell Victor. He's a, mad scientist villain, so his name is Vector for a reason. He says magnitude and direction for a reason. It's all intertwined together. I know, when you start to catch all the cartoons. All right, so we have a vector, right? It gives us distance and direction. It does not give us location, okay? Location has nothing to do with vectors. Then we have a geometrical representation. And anytime geometry is referred to, it doesn't mean like we're going back to the old school geometry stuff. It just means visually, like pictorially, physically, what is it? That's the geometrical representation. So a vector can be represented geometrically using a directed line segment, which looks like this. What else did you do in geometry that looked like an arrow? What was it called? A ray. If this was a ray, what does this arrow mean? That it continues on forever and ever, right? But for a vector, that is not what that means. This just gives us the direction. But the vector is exactly this size. It does not continue on. So a vector and array are not the same thing, okay? In this vector here, point P is the initial point, or the tail, and the Q is the terminal point, or the tip. Welcome to class. All right, so the initial point or tail, and Q is the terminal point. Okay, so you start at the initial point, you end at the terminal point. And there's not always a point after the arrow either. Those are just literally what might be there. Okay, so when we name them, vectors are denoted using the arrow symbol. They're named a lot like rays as well. Just like with the ray, for a vector, you have the initial point is the first letter, the terminal point is the second letter. These little line segments with a little tiny dot, these are actually arrows that did not print well at all. So all of those are arrows that you can't really tell what they are. So we could have vector PQ, or you could have a lowercase p, because that's what this name is right here, with the arrow over it. That's not okay for a ray. It is okay for a vector. Or it could just be a bold-faced lowercase letter. When you're writing it, it's hard to make that bold face, so we're going to use the arrows, but you might see it actually printed that way. Okay. So we want to start with the magnitude. The magnitude, given a vector with initial point x1, y1, terminal point x2, y2. The magnitude of v. Magnitude can be found using the distance formula. Okay, it's just the distance between 2 points. The distance formula is created from what? Where does the distance formula come from? Pythagorean theorem. Because you can put it into, rectangular coordinates like that. So when you're remembering that, okay, it comes from the Pythagorean theorem, and you don't have a formula chart, but you can create it from a concept. You can't just go like, I have no idea what it was. That was so confusing. You know it's a big old square root. And then you know it comes from Pythagorean theorem. Pythagorean theorem is something squared plus something squared. You at least know that much, right? So this is how you build something from a concept and don't just freak out because you don't know the formula. Then you never mix x and y, and you want to find the difference between the two. So this is x2 minus x1 and y2 minus y1, and that's your distance formula. Okay? It looks yucky, but if you think about where it comes from and what it means, it's not that bad. So let's look at number 2. I want the magnitude, which looks like a double absolute value sign. The magnitude of vector RS. So this is going to be y2 minus y1. It's going to be 3 minus a negative, not 3, I'm sorry, I'm making up numbers now. a 5. I don't know where 3 came from. 5 minus a negative 3 squared plus 6 minus 10 squared. This is not why I had you get the calculator, so don't do this on the calculator. That ends up giving me the square root of 80, right? When you simplify the square roots, learn how to do it quicker. It doesn't always have to be a full factor tree or a full birthday cake or whatever it is you want to call it. The easiest way to do it is to find the biggest perfect square that divides into there. But you don't have to always sit there and think about that even. When I take the square root of 80, I know 4 divides into that, and that's a perfect square, so that's something, right? And then this is 20. Well, then this can become 4, and then 5 is a prime number. So even though this is a perfect square, that doesn't even matter because there's 2 of them, and so I get 4 square root of 5. And the more you do that stuff, the easier it is to even do that in your head. Like some of you don't even need to write that stuff down, and you're done. Although sometimes it's safer. Do that. Questions? That's basically distance formula. I mean, come on. Why are there 2 what? Yes, it's not absolute value, it's the magnitude. That's the notation for magnitude. How do you notate it in physics? Because there's different ways to notate it. You don't. You don't do notation. You just put that the vector equals that? Interesting. Okay. Okay, well that makes sense. Okay. But it's not absolute value. It looks like a double absolute value. That denotes magnitude. Does that make sense? So like the vector would equal something else. The magnitude of this vector equals this number right here. The length. Okay, that's a good question. All right, so y'all do number 3. You don't need me. Do number 3. Okay, get to the square root before you simplify, and then I want to talk to you about that. All right, so the square root of 325. Anytime you can think in terms of money, think in terms of money. How many quarters are in $3.25? Think about that. 13, right? Because you got 4 for each dollar, so there's 13. So that means this is 25 times 13. This is a prime number. You take the square root. It's 5 times the square root of 13. Think smarter, not harder. Think in terms of money as often as you can. Y'all can make change and shuffle out money pretty quickly and easily, right? Anytime you can think in terms of quarters, y'all can think in terms of quarters, right? Sometimes that's easier than thinking in terms of other things. Just another way to look at it. We good? All right, so then we don't need to do number 4. I'm going to give you the definition of a zero vector. A zero vector is a vector with magnitude of 0. So it's not a very helpful vector, but it at least deserves a definition, I guess. So there's your definition of a zero vector. Yeah, a lot of things are. Okay. Alrighty, flip it over on the back. Let's talk about different types of vectors. We can have parallel vectors. They have the same or opposite direction, but not necessarily the same magnitude. They could, but not necessarily. So parallel vectors could look like this. This could be A and then B. So if those are my 2 vectors, then I can say vector A is parallel to vector B. Then I have equivalent vectors. They have the same magnitude and direction. So they would look something like this. that you could say then that vector M is equal to vector N? Mm-hmm. Yes, the arrow always goes the same way. It's a good question. And then opposite vectors have the same magnitude but opposite directions. So it would look something like this. This is U and this is B. And then opposite vector, so if A, the opposite of A is negative A, so we could say that U is, vector U is equal to negative of the vector B. We'll talk about what to do with the negatives later, but they have the same magnitude, different directions. Any questions at all? In all three cases, they're parallel though. These are parallel and go in opposite directions, have the same magnitude. These are parallel and they go in the same direction. Those are just parallel. Now, when you look at this graph, right here, something kind of weird happens, which happens even worse on the assignment. If you look at this letter right here, it kind of looks like E because of the line on the grid. It really looks like an E on the homework. But if you find E, like this is C, and if you find E, if you find them both, the E is obvious that it's E. So then the other one is C. So just make sure you're not answering the questions wrong because you're looking at the wrong letter. Those are the only ones that are funky. It just happens to be where it lands. All right, so we're gonna classify each pair of these vectors. So we're gonna start with A and E. So here's A. Here's E. So what do you think about those? Opposite. They have the same magnitude. You don't even have to know what it is. You can count it with slope. Slope won't give you the magnitude, but it tells you they're the same. And so these are opposite. Okay. Then I and F. Here's I. Here's F. Equivalent. They have the same slope and the same magnitude, and they're going in the same direction, so these are equivalent, which is a fancy way to say equal. All right, so then we're going to look at D and E. Here is D. Here is E. Parallel, because they do have the same slope. Okay, they can't just look like they do, but they do. If you count it, they just don't have the same magnitude, so they are parallel. Alrighty, and then B and G. So here's G, here's B. None, right? It's not anything because they're not even parallel, so this is just none. And then we're left with C and H. Here is C, here is H, and they are opposite because they have the same magnitude. Okay, what questions do you have right now? Anything? Easy enough so far? What was the question? Oh, okay. Well, thanks. All right, so we want to prove vectors are equivalent. It says you can show two vectors are equivalent if they have the same magnitude or the same direction. So this here is a true statement. And the distance formula will tell us if they have the same magnitude, right? Will the slope formula actually tell us if they have the same direction? No, it'll tell us that they're either the same direction or the opposite direction, but it will not give us this. So this actually doesn't give us that, and this takes a whole lot of work that is completely unnecessary anyway, so we are skipping that part. Not because the statement is wrong, but because the math behind this is wrong and unnecessary anyway, because we're going to have an easier way to do it in just a minute. Okay, we good? All right, go to your next piece of paper. 142. Okay, so remember that vectors give us distance and direction. They do not give us location, right? But we can have specific locations for them. One of them being standard position. So standard position is when the initial point or the tail of a vector is at the origin. Then it's in standard position, like in that picture over there. Does not always have to be in standard position, but it can be, and that's maybe how you, it's a good way to think about it when you're trying to think about the angles, like it being in standard position. If that is the case, then this point AB here would be our terminal point, obviously. So it says if a vector V in standard position with terminal point AB, then you have a component form. Vocabulary is important, so you got to know what component form means. This vector would just be equal to AB with the pointy brackets. Pointy brackets means it's not a point that you go plot. It's a vector that could be located anywhere, and wherever you start from, you go to the right A, you go up B, or left and down if it's negative. Easy enough? So we have the magnitude and direction angle of a vector in component form can be found using the following. Well, if this is my vector in component form, and this point that to the terminal point is AB, then again, I can set up a little triangle here. This is A, this is B. Doing this is almost exactly the same as converting from rectangular to polar points. So your magnitude V, magnitude of the vector V rather, is just equal to, it's like Pythagorean theorem. It's the square root of A squared plus B squared. It's just like when we found the radius, it's just not X and Y, it's A and B, but they mean the same thing. Okay, easy enough? Then I got to find the angle. If I want the angle in terms of A and B, that's my opposite and adjacent, so it's tangent. So this is going to be the tangent inverse of what? Is it B over A or A over B? B over A, because it was like Y over X, right? Exact same thing you do to convert from rectangular to polar, because they're all intertwined. Okay? We good? All right, so let's look at number 1. We're going to find the magnitude and direction angle for each vector, and it's in component form already. So my magnitude of vector R is equal to the square root of 7 squared plus 24 squared. Still not why I had you get your calculator, but you can use it just to make this part go faster, because I know you can actually do it without it. This is also a Pythagorean triple, but what do we get? 25. It's Pythagorean triple is 7, 24, 25. And if you don't know the triples, it's fine, because it's an easy Pythagorean theorem to work out anyway. But this is my magnitude. Then theta is the tangent inverse of 24 over 7. This is why I had you get the calculator, because that's not a special angle. We are working in degrees with vectors, so make sure your calculator is in degrees. If it's not, or you're not sure, just do shift, it is shift, right? Shift mode, and then pick whatever number is degrees. And you should get 73.740. All right. What questions do you have? All right, y'all do number 2. What do we get for the magnitude? Square root of 10. And then what do we get for the angle? Do we all agree with that? Okay, so what if I were to tell you that that angle is incorrect? Are you sure you typed in -1 over -3? Okay. You did or you didn't? You did, okay, that's okay. So one of the things that we have to pay attention to, which a lot of people ignored on that last test, like you can do the math, you can do this stuff, but what quadrant you were referring to is super important. This vector isn't necessarily in any quadrant that, you know, well, it has to be in a quadrant, I guess, but it's not necessarily in a specific quadrant that you're looking for. But this -3, -1 would be directed this way. So the direction of the vector is towards the third quadrant, right? So if I'm going to rotate from 0, we're talking about I want a third quadrant angle. The calculator gave me a first quadrant angle. So if I have a first quadrant angle, but I want the third quadrant angle, what do I do? Add 180. So I just add 180 and I get 198.435. The reason that you're adding that, that's like when if you'd have gotten pi fourths and I said, okay, it's pi fourths, but we want our third quadrant pi fourths angle. Like y'all are on that, but then this has been confusing people a lot. So every time I myself draw a little picture. This is where I am. This is where I want to be. What do I have to do to get there? Okay, does that make sense? Make sure you're paying attention to that quadrant because I want quadrant 3 here. Okay. And then this first one, this was quadrant 1, and that's what the calculator gave me. That's why we were fine there. All right, let's do number 3. Magnitude of V is equal to the square root 8 squared plus a -12 squared. So it's going to give me, let me just do it this way. Magnitude of V, what do I get in the end for that? 4 squared of 13, good. All right, so then I need theta. Theta is equal to the tangent inverse of -12 over 8. So when you do that, it gives you -56 something, right? Okay, make sure that that's what you get. You actually do that. This right here is directed towards which quadrant? The fourth, right? This is quadrant 4. This angle right here, what quadrant is that in? Look, 0, 90, 180, 270, right. So it's going to be in the fourth quadrant, and I want to be in the fourth quadrant. The problem is this is negative, and I want my angles to be positive. So if I'm already in the fourth quadrant, but with a negative angle, what do I do to that number to get the positive number I want? Add 360. So you can just do plus 360 in your calculator, and you get 303.690. So remember when we started the radians, you're like, oh my God, those are so hard. But isn't it easier to think about radians as you go around the circle than it is the degrees? It's a little bit easier, Melissa. Yeah, I know. All right, so y'all do number 4. Let's just make sure that we got this whole quadrant thing down and all this before we move on. We're not going to do all of them, but do that one. Okay, so the calculator gives you, for the theta, it gives you like negative what? 28 something? What quadrant is this directed towards? The second, good. So they gave me a fourth quadrant angle. I want a second quadrant angle, so what do? Add 180. So it's going to be 151.390. And every time the calculator is either going to give you a first or a fourth quadrant angle. Because when you take the inverse of tangent, that's all you can get, right? Either first or fourth, and then you figure out which quadrant you want to be in from there. Okay. What questions do you have? All right. Let's flip it over then. We don't need to do the last two. Okay, so that was standard position, but really that same stuff applies even if it's not in standard position. This dotted line right here represents a standard position vector. This just represents some other vector. Now, if I move this vector without turning it and changing the angle, obviously these points would change, but the vector itself, as it written as a vector, doesn't change. The vector is the same because the position, it could be anywhere. So it says any vector with initial point x1, y1 and terminal point x2, y2 can be written in component form as, all right, so again, vocabulary is important. Component form has the little pointy brackets. This is also the only time I can think of so far where you've had an x1, y1, x2, y2 situation where the order matters. Because when you do slope, if you mix up x1, y1, and x2, y2, it doesn't matter. You can just pick whichever one you want. Same thing for distance formula and a lot of the other stuff that you've done. But here it matters. It didn't matter for slope because you make a fraction, the sign takes care of itself. Doesn't matter for distance formula because you square it and the sign takes care of itself. But here, you have an initial point and a terminal point, and if you subtract them backwards, your vector is going to be going the wrong way and you're wrong. So you have to make sure that when you have it written, that you're actually subtracting the correct way. So our vector then, in component form, looks like this. x2 minus x1, and then y2 minus y1. Basically, you just subtract the x's, subtract the y's, make sure they're in the correct order, and that was really what was underneath the distance formula anyway. So when you have a vector, the way it's written, this vector CD, C is the initial point, D is the terminal point. So C has to be your x1, y1, and D has to be your x2, y2. So that when you subtract, it's got to be 6 minus 3, and then 3 minus 5 to get you vector CD, which is 3, negative 2. Okay. Easy enough? These ordered pairs clearly give us location. That's the idea of a coordinate pairs like that. This gives me a vector, but it doesn't tell me where it is. Now, you do number 8. It should be fairly simple. Oh, yeah, thank you. B is supposed to be S, or it makes no sense at all. And watch your signs. This stuff is easy, but it's so easy to mess up on a sign. Any questions? All right. We are going to jump to number 10 then. All right. So it's asking us here, it says, give the component form, magnitude, and direction angle for each vector. So the first thing I want to do for vector AB is come up with the component form. That means this is going to be negative 4 minus 9, negative 1 minus a negative 3. So vector AB is negative 13, 2. That's my component form. Now, everything is easier to do from component form instead of doing from the coordinates, A and B. So when I find magnitude, if I wanted to use the coordinates like we did on that first piece of paper, I do distance formula. If I have this, then I can just say that the magnitude of AB is equal to the square root of, and that's a squared plus b squared, so negative 13 squared plus 2 squared. What does that give me? Square root of what? 173. Yeah, it doesn't reduce. Might as well just leave it like that. So I have my component form, I have my magnitude. Now I need theta, which is the tangent inverse of 2 over negative 13. And this, I want, what quadrant am I referring to here? Second, so it's quadrant 2. So since it's negative, it's going to give me quadrant 4, and I add 180. Make sure you're actually getting these numbers and don't just copy them down. And if you're not getting them, please make sure you say something. What questions do you have? Give a second to finish. Whoops. Turn it off, please. Oh, there you go again. Oh, that's okay. Just draw an arrow because we're not doing the other one. All right, we good? All right, so you're going to do number 12. Not 11, do 12, the one with the graph. 12. Okay. Said people doing the wrong one all day. 12. Yeah, you can, as long as you get your signs in there correctly. It's fine. Because you won't be given the pictures all the time. Let me know if you're stuck or confused or both. When you're thinking about the angle, if you look at the vector lives in quadrants 1 and 2, and that arrow does not mean that it's continuing on forever. But where the vector is placed means nothing as far as the angle is concerned. This is directed towards the 4th quadrant, so it is a 4th quadrant angle that would rotate us around to get us to that direction. Okay, so keep that in mind. Yes, so the vector itself is in quadrants 1 and 2, right? But that has nothing to do with what quadrant we're wanting our angle to be in. It has to do with where this is directed towards. Because if you think about what this is giving us is the angle that it takes to rotate this, and we always start right here. So I'd have to rotate around to a quadrant 4 angle to go in this direction. Does that make sense? So just think about where it's pointing, basically. All right, what questions do you have? We good? Everybody okay on quadrants and whatnot? Because if you can do, I mean, you can do the work is whatever, but make sure you know how to pick the quadrants. Okay, so here's another thing about equivalent vectors. Remember the stuff we marked off on the first page where it would have taken a ton of work that we don't necessarily need to do because it says vectors are equivalent if and only if they have the same component form. Your component form gives you distance and direction. So I've got whatever it is, it's going to be the same if they have the same component form. So we're going to use that to figure out if these are equivalent vectors. So I'm first going to find AB, which should be easy. So we -7, oh, I totally wrote a 3. -7 minus a -3, -2 minus 6, which gives me -4, -8. By itself means nothing. Got to have something to compare it to. So then I've got CD. That's going to be -1 minus 3, -9 minus a -1. It's going to give me -4, -8. So the locations were clearly different because my ordered pairs were different. The component form, exactly the same. So it has the same distance, same direction. That means that vector AB is equal to vector CD. There's my little statement there. Questions? All right, so this is simple, I know, but I still want you to do 14 while I hand out the assignment because I want to talk about something that happens in it. So it should be easy for you to do. Hopefully that part's not super confusing. So you get 9, negative 6, and 9, 6, right? So they're not the same, right? Which I know you can figure out. So to say that they're not, we have vector AB is not equal to vector CD. Then earlier I had somebody ask me, okay, does that mean then that these are opposite vectors? So are these opposite? Vector AB, that 9, negative 6, is going to be directed this way. CD, which is 9, 6, is directed this way. They do have the same magnitude, because if I put it in a little magnitude form, I'm going to get the same thing. But they are not opposite and they are not parallel. So they're not equivalent. They're not, because it has more to do with just with the magnitude. Plus, remember for opposite, U has to be equal to negative V. So if that was negative 9, negative 6, that would be different than they would be opposite. Okay. That question doesn't ask you. All it asks you is if they're equivalent. That was just a good thing to talk about. What questions you got? All righty. Go ahead and you can get this glued in your eyes and grab the homework real quick though, because don't forget to check on E and C so you're looking at the right letters. And then there's 2 9 and 10s. You're eliminating the second 9 and 10. Yes. I just said 9 and 10 second period, and I saw people marking this off. I'm like, what are you doing? I didn't realize there was 2. So it's this one you want to eliminate, because this is the part we eliminated on the notes. Okay. All right. There we go. There was a back. There were 2 sheets of notes. I think it warrants a back. All right.